Hello and welcome to our second to last week of ECE 108. This week we're going to continue our discussion of conditional probability and independent events by giving a few examples in this lecture. In the next lecture we'll talk about Bayes' theorem with a bunch of applications. And then finally in lecture 30 we're going to talk about expectation and give some applications of expectation. So without further ado, let's jump into it. Okay, so suppose I toss a coin twice, and the events that I get a heads versus heads tail versus head tails versus tails heads are all equally likely. And now we're going to let A be the event that the first toss lands heads, and I'm going to let B be the event that the two tosses land differently. I could ask a natural question: are the events A and B independent? So when thinking about independence, it's natural to try to think things out logically, but generally speaking, there's a lot of fallacies that you can fall into if you try to tackle problems in that way. So instead of trying to argue that one result doesn't necessarily affect the other result in this case, what we're going to do is simply apply to the definition. So one way that I can do that is I can first say, if I can show that the probability of A intersect B is equal to the sum of, or the product of these probabilities here, then I am done. So to do this, I can directly compute everything. So a direct computation will give me that the probability of A, well, what's A? Well, A is the event that the first toss lands heads. So what would that be? Well, if I look at the sample space, this term here and this term here are the only elements of the sample space that start with the H. Therefore, the probability of A is simply the same thing as the probability of this set here. Well, there's two elements here and there's four elements here, and I've been told that these various events are all equally likely. Therefore, I can use the uniform probability distribution, and I'd say this probability is simply 1/2. Now I can do a similar thing for B. B is the event that the two tosses land differently, so the probability of B will simply be the probability of the set that these two events here occur. So explicitly, this probability here, and again, uniformly distributed, so this is simply going to be 1/2. If things weren't uniformly distributed, then I would want to use the fact that these various events, say heads, tails, are mutually exclusive, and then I could say, well, that's the probability of heads plus the probability of heads tails. Okay, so now the last thing I want to compute is what is the probability of A intersect B? Well, this is pretty trivial to do. I know A intersect B is simply equal to, well, A is this set of these two events, and B is the set of these two events. The only thing they have in common is heads tails, so this will simply be the probability of heads tails, which is simply equal to 1/4. So now from here, I can simply notice as 1/4 is equal to 1/2 times 1/2, it follows that these events are independent. So explicitly, this probability times this probability is equal to the probability of the intersection, which is the definition of independence. So solution 2, I'm doing the exact same thing in this case, other than I'm applying one of the other equivalent definitions of independent events. So in particular, if I show that the probability of A is equal to the probability of A given B, then I'm done. So also note, instead of proving this statement here, I could have proven that the probability of B is equal to the probability of B given A, and that would also show independence. So in this case, I need to compute the probability of A, which I've already done, so that's just 1/2. And now I need to compute the probability of A given B. Well, what's this? This, by definition, is the probability of A intersect B, all divided by the probability of B. So again, this is just the definition of the probability of A given B. So from here, the probability of A intersect B, well, I'd have to go through the process of computing that, but I've done that before. I know that that is simply the probability of heads tails. And the probability of B, well, I'd still have to compute that if I were doing this solution method from scratch, but I already know that that's the probability up here. So this is simply equal to this, and then I know this probability is 1/4, this probability is 1/2, so it's 1/4 divided by 2/4 if I want, and then that is just 1/2. So the probability of A is equal to the probability of A given B, therefore these events are independent. So generally speaking, you can use either of these methods or replacing A with B and B with A here to show that two events are independent. So you have a few choices, but ultimately you end up having to do the same work either way. So just keep that in mind. Now let's go on to another example. So consider a coin where the probability of heads is some unknown probability p, such that it's between 0 and 1, not including 0 or 1. So I have a coin where I don't know what the probability of it getting heads is, but I do know that it can sometimes be heads and it can sometimes be tails. That's the key idea here. So in addition to this, suppose that it is known that the coin tosses are independent. So if I flip the coin once, that does not affect the probability of the results when I flip the coin a second time. Generally speaking, you can usually assume independence of things like coin tosses or dice rolls, but you should keep in mind that you do actually need this for the method that I'm going to use to work. So you do have to mention it somewhere. Okay, we want to devise a way to get a fair toss from this coin. Okay, so the coin's not necessarily fair. How can I build a way to find a fair toss out of this unfair coin, or potentially unfair coin? Well, solution. Even though the individual rolls are potentially biased, if, and as of now it is an if we can find two events that are equally likely, and if we can differentiate between heads and tails for these events, then we can generate a fair toss. So before I get into the details of how we can actually generate this fair toss, let's find two such events that are equally likely and allow me to differentiate between heads and tails. So notice that the probability that heads comes up followed by a tails, well, since these events are independent, that's simply going to be the probability of heads times the probability of tails. Now, these things here are just real numbers. Multiplication of real numbers is commutative. Therefore, I can say this is the same thing as the probability of tails times the probability of heads. But again, these are independent events, so by definition, this is the probability of tails followed by a heads. So these two events here have the same probability. I don't know what it is. It's going to be p times 1 minus p, whatever that is, but I do know that the events are equally likely. Further, in this event, heads comes first, whereas in this event, tails comes first. Therefore, I can differentiate between heads and tails for these two events. So, filling this out, thus heads and tails are equally likely events, and note that the order of these results are different. So now I can use these two facts together, and I can now repeatedly toss the coin, and I'm going to do this until I have two flips with different results. At this point, I can pick either the first result or the second result, and again, this has to be chosen before I flip the coin as my fair result. So for instance, I flip it, tails, 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 heads. I could say, oh, I was going to pick the first one, so therefore it's tails, that type of a thing. So now for coins, in practice, this method works rather well, but it also can work with things like dice rolls. In the case of dice rolls, it's not as practically effective, but you can generalize this method to work for dice rolls, and you will in fact do that on one of your homework problems. Okay, so let's look at another example. A standard pack of 52 cards includes 12 face cards. So here the face cards are Jack, Queen, and King. Everything else is a non-face card. Suppose you draw two random cards and notice that the first is not a face card. What is the probability that the second card is a face card? Well, let's look at how I could possibly go about doing this. So, solution. We want to know the probability that the second card is a face card, given that the first card is not a face card. So in order to make this problem a little bit easier, let's give these things symbols. So let A be the event that the first card is not a face card, and we're going to let B be the event that the second card is a face card. Okay, so what probability do I want to compute? Well, I want the probability that the second card is a face card, but I also have extra information in that I know the first card is not a face card. So this is a conditional probability problem. So in particular, I want to know what B is given that A occurred. So again, the probability that B happens given that A happened. Well, by definition, we know this thing is simply going to be the probability of A intersect B, all divided by the probability of A. So now I simply need to compute these two probabilities and compute the ratio, and then I am done. So let's examine this top probability here. So the probability of B intersect A is the probability that 1, the first card we pick is not a face card, and 2, the second card is a face card. So what do I know about these cards? Well, generally speaking, if I'm talking about cards, unless I tell you it's biased, we're assuming that they're uniformly shuffled, and the probability distribution of getting any particular card is uniform. So from here, I can say that the probability of B intersect A will simply be given by this expression here, just coming from the fact that these cards are uniformly distributed. So namely, it's going to be the number of ways that the first card can be picked to be not a face card, and the second card can be picked to be a face card, all divided by the number of ways that I can pick 2 cards out of this deck of 52. So what is the number of ways that A can happen? Well, A is the event that I pick a card and it's not a face card, and there are 12 face cards, so the number of ways that A can be picked, so the number of ways that the event A can happen will simply be 52 minus 12. Okay, so here from this, I get this thing is 52 minus 12. That's the number of ways that I can get A to occur. What about B? Well, there's only 12 face cards, and B is the probability that the second one is a face card. So this thing, the number of ways that I can pick a face card, is exactly 12. Finally, the number of ways that I can pick 2 cards out of a deck of 52, well, there's 52 ways that I can pick the first card, and there's 51 ways that I can pick the second card, so the number of ways that I can pick this will simply be this product. So if I put all of this together, I end up with this expression here. So now I can further simplify this expression just by doing some arithmetic, and I get that this is 40 times 12 divided by this statement here. So this is the probability that A and B both occur. Now I need to know what is the probability that A occurs on its own. Well, again, there's exactly 40 cards that are not face cards, and I'm picking the first card out of the deck, so the probability of A will simply be 40, the number of ways that I can pick a non-face card, divided by 52, the number of ways that I can pick the first card out of the deck. So this will simply be 40 over 52. So from here, I can put all of this together. Thus, the probability of B given A is simply this expression here. So again, just take this thing, divide it by this. And now instead of plugging this into a calculator, I can do some simple arithmetic. When I divide by a fraction, I can flip and multiply. And from here, the 52 cancels this 52. So explicitly, these cancel, and these two 40s cancel. So once I do that simplification there, I simply get 12 divided by 51 for my solution here. Okay, so that's another good example of a conditional probability question. Let's look at another independence question. So in the previous example, are the events of first drawing a non-face card and then drawing a face card independent or not? Well, again, I have multiple ways that I can show independence. And here, since I've done some work on the previous slide, I'm going to use that to determine which one of the methods I'm going to use. Okay, so solution. Again, let A be the event that the first card is not a face card, and let B be the event that the second card is a face card. So from the previous work, I know that the probability of B given A is 12 divided by 51. Okay, so I already know this. So if I want to show independence, the kind of easiest way forward at this point is to simply compute the probability that B occurs and see if it's the same as the probability of B given A. If it is, they're independent. If it's not, they're not independent. So now, how would I possibly go about computing the event that the second card is not a face card? Well, there's a natural trick that you can use that might not be intuitive when you first see it, but after you first see it, you should always have this trick in mind whenever you're trying to compute the probability of any given event B. Well, we're going to first note that B as a set is the union of these two sets. And as we go through the problem, you'll see how this makes the problem easier to solve. Okay, so since b is equal to this, I know that the probability of b is the probability of this thing here. It's the same set, so I can replace that. So computing this gives me that the probability of this union, again, these are mutually exclusive basically by definition of the complement. So this is simply going to be equal to the probability of this event plus the probability of this event, and this is coming from axiom 3. So now I know that these events of picking cards are uniformly distributed, so I can compute these probabilities here by invoking the uniform distribution. So namely, the probability that A intersect B occurs will simply be the cardinality of A intersect B divided by the ways to pick 2 cards, and the probability that A intersect B complement occurs will simply be the cardinality of A intersect or B intersect A complement, all divided by the number of ways to pick 2 cards, and again I add these because I have a sum there. So now I can compute these terms pretty straightforward at this point. So B intersect A, its cardinality we computed earlier. That was just 40 times 12. So again, there's 12 ways that I can pick a face card, and there's 40 ways that I can pick a non-face card. Therefore, this cardinality, the intersection, will simply be 40 times 12. And next, again, the number of ways that I can pick 2 cards, that's simply 52 for the first card times 51 for the second card. So to this, I want to add the cardinality of B intersect A complement. Well, a complement would be the statement that the first event is a face card. So for a complement, if I did a complement here, I would get rid of this not, right? So from here, the number of ways that the first card can be a face card is 12. And for B, that would be the number of ways that the second card can be a face card. And now that would be 11 since I already picked a face card. So from here, I'd have 12 times 11, all divided by this thing here. So now at this point, I can add these together. That's straightforward. You've added fractions before. And when you add that and do the simplification, you end up finding that this is exactly 12 divided by 52. Okay, and 12 divided by 52, is that the same thing as 12 divided by 51? Well, no. So these events are not independent from each other. Okay, so this might seem counterintuitive, but let's think of this another way. Say if I have a mixed deck of cards, and I just lay these cards out. So here's my bunch of cards, and assume there's 52 of these. And then what if I asked you, what is the probability that pick any card in this list is a face card? Well, there's 12 face cards and there's 52 cards, so the probability that any given card is a face card is 12 divided by 52. It doesn't matter if it's the first card or the second card or the 52nd card. The probability that each card is a face card is the same, and that's exactly what I was asking here. What's the probability that the second card is a face card? Okay, so let's now examine a new example, the Monty Hall problem. So here I'm just going to state the problem here, and I'm going to answer it in Mr. Paint. So you're on a game show, and there's 3 curtains labeled 1, 2, and 3. So you get to pick one of these curtains. Behind 2 curtains, there is a goat, and behind the third, there is the thing you desire most. Now, after you pick your curtain, so after you say, this is my curtain, it is revealed that the prize is not behind one of the curtains that you did not pick. And now you're also given the option to switch curtains. So you can change from the curtain that you picked or the remaining curtain. So the question is, should you do this switch? Well, how would we go about computing this? A natural way of doing it is to compute the probability that it's in the first curtain that I picked and compare that to the probability that it's in the remaining curtain after I'm told which one of the curtains had a goat behind it. Okay, so now I have my 3 curtains. Behind one of them is a prize. Behind the other 2 are goats. So let's just assume without loss of generality that I pick this first curtain here. Okay, so what is the probability that the prize is behind the curtain that I chose? Well, the probability that the prize is behind 1 is simply going to be equal to Well, the number of locations where the prize could be, that's going to be 3, so I divide by 3 here. And the number of ways that the prize can be behind curtain 1, well, that's just 1, so it's going to be 1/3. So further, I can note here that the probability that I chose wrong, so namely the probability that the goat is in either of these cases here, is going to be the probability that it's in p is equal to 2 or 3, and that's going to be 2 all divided by 3. Okay, so now Monty comes through and he tells me that, say in 3, we have a goat. And he gives me the option to stay or to switch. So if I stay, I know my probability is 1/3, but if I switch, what would my probability be? Well, Monty gives me privileged information. He only tells me where a goat is. He never tells me where the treasure is. Thus, since he can never reveal the location of the treasure, by telling me that it's not in 3, that tells me that there's a 1 in 3 chance that it's in 1, and there's a 2 in 3 chance that it is now in 2. So from here, the probability that it's actually in 2 is exactly equal to 2/3. So here I should definitely switch because it increases my chances of getting the goat. So now let's just look at the slide version of this just to see the basic argument once again. So we want to know if the probability that the curtain we picked is greater than the curtain that we have the option to switch to. If it is, we should stay. If it's not, we should switch. The probability that our curtain is correct is 1/3, again, since there's 3 curtains and only 1 prize. And next, the probability that we did not pick the right curtain is now going to be 2/3. So out of this 2/3 option of it being in 2 or 3, Monty then will always only tell me that it's not in one of the particular curtains. So once Monty tells me which one of the 2 curtains that it's not in, the remaining option has a 2/3 chance of having the prize. Thus, if I do switch, I now have a 2/3 chance that I would get the prize. And yeah, that's the basic idea here. If you try to tackle it with straight probability, we will see this again where we tackle it using Bayes' theorem, which is a lot stronger of an argument. So you definitely should switch in these cases. So before we head off, I have built a script that actually simulates this Monty Hall problem just to show you, 1, how you could potentially do that, and 2, that numerically we get results that agree with these analytic results that I've mentioned here. So it's kind of there to fix the haters. So skipping over the details of the coding, here when I ran 10 to the 7th simulation, I had a 33.324 chance of getting it if I stayed, and a 66.67 if I switched. So notice these aren't exactly 1/3 and 2/3. Again, that's just statistics for you. But again, this is very close to what I got analytically, and this is evidence that my analytic solution is in fact correct. It's not a proof, but since I'm brute force simulating these cases, if you didn't like the previous argument, this is a separate justification for you. So yeah, again, we're going to revisit this question in the next lecture once we have a better technique to tackle this question. So just keep that in mind, but that's the basic idea here. So it is noteworthy that this Monty Hall problem was quite controversial back in its day. Okay, so for your assigned reading, I want you to read pages 84 through 86. So here I was a bit lazy with my prep of lectures, and I took the examples directly out of the book. But if you want to do the reading, it's there for you. Okay, so for the meme, here, and my yard has so much grass, and I'll teach you all kinds of tricks, and yeah, we don't care about the problem. We get a goat. That's awesome. Okay, so I will talk to you all next lecture, and I hope you have a wonderful day.